Come on, my dears, we proceed further in chapter number 2. Today we are going to study the analysis of different 11 AC circuits, out of which in textbook you will find analysis of only 7 circuits, and that too they have not explained properly and the analysis is also incomplete. We will see complete analysis of all 11 circuits. Okay, any of these 11 circuits may be asked in the board examination, and you are given notes for this, so you constantly try to refer that notes. As and when I just instruct you to refer particular circuit, you please do that. Okay, now be very attentive on screen. Analysis of different AC circuits. My dears, first of all, recall the formula of tan delta. What was the tan delta formula? XL minus XC upon R. How? Did you derive formula of complex impedance of AC circuit? Yes, it was this: Z equals to R plus J into XL minus XC. And now tell me, what is tan delta formula? It is imaginary part upon real part. What is imaginary part here? Coefficient of plus J, it is XL minus XC. So this is imaginary part upon real part, which is R. So if tan delta is XL minus XC upon R, find out delta. It will be tan inverse of XL minus XC upon R. Tan inverse of XL minus XC upon R. Now I am showing you very easy way. In all 11 circuits, there are only 5 different values of delta. Only 5 values for delta. Look, either 0 or positive or negative or plus pi by 2 or minus pi by 2. I repeat, which are the 5 values of delta? Come on, 0 or positive or negative or plus pi by 2 or minus pi by 2. In which case, which value is applicable? I am showing you. If it is tan inverse of 0, this part is suppose 0. How it is 0? I will show you. If this part is 0, then tan inverse of 0, then delta is 0. Tan inverse of 0, delta is 0. Tan inverse of positive number, delta is positive. Tan inverse of negative number, delta is negative. Tan inverse of plus infinity, delta is plus pi by 2 radian. Tan inverse of minus infinity, delta is minus pi by 2 radian. I repeat, tan inverse of 0, delta is 0. Tan inverse of positive number, delta is positive. Tan inverse of negative number, delta is negative. Tan inverse of plus infinity, delta is plus pi by 2 radian. Tan inverse of minus infinity, delta is minus pi by 2 radian. Got it? Fine. Now we will finish this analysis for each circuit in 4 different parts. In first part, we will write certain formula. Then in second part, we will draw phase diagram. In the third part, we will pass some comment regarding phase relationship between voltage and current. And in the fourth part, we will draw graphs of voltage and current versus omega t. Let us see all the 4 parts for first circuit. What is that first circuit? Look here. I have made a list of all 11 circuits. You please refer this circuit number 1. It is RLC in series where XL greater than XC. Okay. Whenever you find L and C together in the same circuit, you are supposed to make a comparison between the magnitudes of their reactances. That is, comparison between XL and XC. That you can make in three different ways, either XL equal to XC, or XL greater than XC, or XL less than XC. XL equals to XC, then resonance will take place. Remaining two possibilities we are going to discuss today, XL greater than XC, XL less than XC. Let us first of all take XL greater than XC. Here it is, look. We are taking the case where XL greater than XC. XL greater than XC, fine, look. First of all, recall the formula of delta. Delta is tan inverse of XL minus XC upon R. Delta is tan inverse of XL minus XC upon R. Right now XL is greater than XC, so this part is positive. Positive upon positive, it will be positive number. Tan inverse of positive number, tan inverse of positive number, then delta will be positive. Delta will be positive. Fine. For all 11 circuits, this alternating voltage formula remains the same. V equals to Vm cos of omega t. For alternating current, last time we had obtained the formula I equals to Im cos of omega t minus delta. Fine. This formula of alternating current you will remember for positive value of delta. If value of delta is negative, then formula of current is I equals to Im cos of omega t plus mod delta. Fine. At present delta is positive, so we should use this formula. Fine. What about mod z? Mod z formula was under root of r square plus xl minus xc whole square. Fine. Now let us go for phase diagram. Phase diagram. My dears, there are certain points to remember for drawing this phase diagram. First, positive x-axis is to be taken as real axis every time. Positive x-axis will be taken as real axis. Whole y-axis should be taken as imaginary axis. Fine. In that, on this positive axis, we will show magnitude of inductive reactance. On this negative axis, we will show magnitude of capacitive reactance. Okay. On this positive x-axis, we always indicate the value of resistance, that is real part of complex impedance. I repeat, R is to be shown on positive x-axis, that is on real axis. XL is always to be shown on positive axis, and XC is always to be shown on negative y axis, always. Fine. Now at present, RLC, everything is there. So we must show in the diagram R also, XL also, XC also. But what is the possibility you have taken at present into consideration? XL greater than XC. XL greater than XC. Now tell me. R I am showing first of all, correct? Whatever value you like, depending upon that, you can show this length, correct? Any length you can take as value of R on x-axis, positive x-axis. Now, because you have taken XL greater than XC, then suppose XL value is, suppose 7 units. Not necessary you should assume 7 units. At present I am assuming 7 units. How? Look, 1, 2, 3, 4, 5, 6, 7. Correct? And XC value, because it is smaller, I take it just say 3 units. How much? 3 units. Look here. 1, 2, 3. Correct? So 7 is greater than 3, means XL is greater than XC. Fine. And now ultimately we require XL minus XC. We require XL minus XC. So you find out that 7 minus 3, that is 4 plus 4. So plus 1 plus 2 plus 3 plus 4. Correct? So this much value is, look here, this much value is, come on, XL minus XC. How much is this much? Come on, XL minus XC. Fine. And once you get XL minus XC, 7 minus C, that is 4. From that point onwards, you should draw horizontal line. and where the value of R ends, from that point onwards you should draw vertical line, and the point of intersection of this horizontal and this vertical line gives us hybrid point capital H, which represents complex impedance in a complex plane. Once you get point H, then you should join it with origin, you will get line segment OH. Distance of hybrid point from origin is going to give you magnitude of complex impedance, fine. For all 11 phase diagrams, remember the current phasor is always to be shown along positive x-axis, always along positive x-axis, it is current phasor, and in the direction of ray OH, you are supposed to draw voltage phasor, fine. This is voltage phasor, this is current phasor, and this is the phase difference between them, it is delta, correct. When delta is positive, you must show it in the first quadrant. Whenever delta is positive, you must show it in the first quadrant. Whenever delta is negative, you must show it in the fourth quadrant. Okay. Right now it is in first quadrant. Okay. Now tell me, what is tan delta from here? Tan delta, opposite to delta divided by adjacent to delta, it is XL minus XC upon R. Here it is. Tan delta equals to XL minus XC upon R. Got it? And what about, according to Pythagoras theorem, measurement of hypotenuse will be equal to square root of summation of squares of remaining two mutually perpendicular sides. So mod Z will be equal to under root of R square plus XL minus XC whole square. Here it is. Mod Z equals to under root of R square plus XL minus XC whole square. Got it? What about third part? About phase. You know delta equals to tan inverse of XL minus XC upon R. Right now XL is greater than XC, bigger value minus smaller value, this will give you positive value, positive upon positive, positive, tan inverse of positive number, and hence delta you will get positive. Whenever delta is positive, just think here, whenever delta is positive, this phase of current is smaller than phase of voltage. If phase of current is smaller, means current is lagging behind in phase, and here phase of voltage is more, means voltage is leading in phase. That is what I have written here, voltage is leading in phase. You must understand, when voltage is leading in phase, current is lagging behind in phase. Okay, fine. And then we go for fourth part. Fourth part is of graphs. We are supposed to plot graph of voltage and current versus omega t. Whenever delta is positive, the graphs of voltage and current are obtained this way. This pink colored graph is the voltage graph, correct? Voltage graph. Because it starts with maximum. You know, time begins to increase from t equal to 0. If you place here first moment t equal to 0, cos 0 is 1, 1 into Vm, that is Vm, which gives you maximum value. So, voltage graph starts from maximum, fine. And then after it goes on decreasing, again goes on increasing, again goes on decreasing, again goes on increasing. That is how it changes periodically according to cos function, fine. Current graph is this, shown with the blue color, okay. Then here, this much angle gives you phase difference between voltage and current. How can we say that voltage is leading in phase? I am showing you. You start with their maxima, and move towards the right hand side this way, correct? When you start from maximum value and when you move towards the right hand side, whichever quantity decreases to 0 first, that quantity is said to be leading in phase. Out of these two, you can see this pink colored graph becomes 0 first. That's why we say that voltage is leading in phase. After some time, current also becomes 0. But after some time, that's why current is lagging behind in phase, voltage is at present leading in phase. Fine. Now, let us begin with the analysis of second circuit now. RLC everything in series, but XL less than XC. XL less than XC. Tell me what are the changes would you like to make? I am showing you. First of all, delta formula we can write this way. Then voltage formula, but because delta is negative, how can we say that delta is negative? I am showing you. Put it here. XL less than XC. XL less than XC. Because XL is less than XC, smaller number minus bigger number will give you negative number. Negative upon positive will be negative. Tan inverse of negative number, here it is. Tan inverse of negative number, then delta is negative. When delta is negative, you must use this formula of alternating current. I equals to Im cos of omega t plus mod delta. This phase is more than this phase by amount mod delta. So, because phase of current is more, current is leading ahead in phase. Come on, mod Z formula, same, under root of R square plus XL minus XC whole square. Fine. Then, we go for this phase diagram. Now, remember the case, XL less than XC. So, this you may show, say, by 3 units, and this you may show by 7 units. But ultimately, what do we require? XL minus XC. So, 3 minus 7, 3 minus 7, that is minus 4. Minus 1, minus 2, minus 3, minus 4. And so, XL minus XC you get here on the negative axis. From this point onwards, you can draw horizontal line, and where the value of R ends, from that point you can just draw vertical line. This horizontal and this vertical line, they intersect at some point, which is giving you hybrid point capital H. Just refer circuit number 2 in the notes. Refer circuit number 2 in the notes. Referred? Can you see point H here in the 4th quadrant? Fine. Now tell me, current phasor is always to be shown on positive x-axis, but if here is the point H, then you can just join it with origin O and then find out ray OH, ray OH. That ray OH will give you voltage phasor. This is current phasor, and angle between voltage phasor and current phasor you refer in the notes. That angle is delta, but the delta appears in the 4th quadrant. When delta appears in the 4th quadrant, naturally it is negative, correct? Fine. Then tell me, whenever delta is negative, you can use these graphs, correct? Look, here when you start from maxima and when you move toward the right hand side, it is the blue colored graph of current which becomes 0 first. Because current becomes 0 first, we say current is leading ahead in phase. When current is leading ahead, you can say voltage is lagging behind, okay? I just suggest you to remember only one thing, delta positive, voltage is leading in phase. Delta negative, voltage is lagging behind in phase, okay? Fine. Now, we go for third circuit in which there is only resistor in AC circuit. Only resistor, okay? Look, only resistor is there, then tell me, from here, these two are not there. If inductor is not there, you can take XL equal to 0. If capacitor is not there, you can take XC equal to 0. Resistor is there. So, these two are not there, so these two are zeros. 0 upon R, 0. Tan inverse of 0, here it is. Tan inverse of 0, then delta is 0. Delta is 0. And when delta is 0, just put it here. Put delta equal to 0 here. So, this phase also will become omega t. This phase is already omega t. So, voltage and current will have same phase. Means they are said to be oscillating with the same phase. Come on. This formula number 4 as it is, no change. Fine. Sorry. In formula number 4, when only resistor is there, inductor and capacitor are not there, you can take XL and XC, both of them 0. When these both are 0, this part will be 0. Under root of R square will be only R. Okay, fine. Now, Come back to this phase diagram. Only R is there. These two are not there. So don't show XL, don't show XC. XL and XC are not to be shown. Only resistance is to be shown. You can select any value of R, and where the value of R gets over, at that very point you can just write capital H, which gives you hybrid point. And if you extend ray OH, it will give you voltage phasor. Current phasor is already in the same direction. So whenever voltage phasor and current phasor point in the same direction, then delta, phase difference between them, is said to be 0. Because delta is 0, they point in the same direction. Fine. Now we go for graphs. Come on, when delta is 0, when delta is 0, these are the graphs. This is pink colored graph is for voltage, blue colored graph is for current. Can you see one thing? Both the values become maximum at a time, 0 at a time, again maximum at a time, becoming 0 at a time. Now tell me, both the values become 0 at a time, maximum at a time, 0 at a time, maximum at a time. That is how they are said to be oscillating with a same phase. Oscillating with a same phase. Fine. Now tell me, we go for now circuit number 4. Circuit number 4 is that in which only inductor is there. Only inductor. Fine. When capacitor is not there, X is 0. When resistance is not there, R is 0. So positive number divided by 0. Positive number divided by 0 will give you plus infinity. Tan inverse of plus infinity. Here it is. Tan inverse of plus infinity. Then delta is plus pi by 2 radian. Delta is plus pi by 2 radian. Put delta equal to plus pi by 2 here. When you put it here, this phase will become omega t minus pi by 2. This phase is omega t. Whenever delta is positive, voltage is leading ahead in phase. And now only inductor is there. So these two are not there. So XL square and its square root will give you only XL. XL means omega L. Correct? And tell me, when only inductor is there, you must show only XL. Only XL. Correct? Resistance and capacitor are not there. So don't show R, don't show XC. Correct? You show only XL. And wherever value of XL gets over, at the same point you may write capital H. And then ray OH you can extend. And in the direction of ray OH, you will get voltage phasor. So situation is this. This is voltage phasor, this is current phasor, this is the angle between them, delta equals to plus pi by 2 radian. Got it? And for delta equals to plus pi by 2 radian, this is the graph. For delta equals to plus pi by 2 radian, these are the graphs. Come on, tell me, when voltage is maximum, current is 0. When voltage becomes 0, current becomes maximum. When voltage becomes maximum, current becomes 0. When voltage becomes 0, current becomes maximum. When voltage becomes maximum, current becomes 0. Look, when voltage is maximum, current is 0. When this becomes 0, this becomes maximum. When this becomes maximum, this becomes 0. When this becomes 0, this becomes maximum. When this becomes maximum, this becomes 0. When this becomes 0, this becomes maximum. That is how they are oscillating with phase difference between them pi by 2 radian. Pi by 2 radian. Fine. Now we consider circuit number 5 in which only capacitor is there. Only capacitor. So only capacitor is there means these two are not there. So 0 minus Xc will give you negative number upon R is also not there. Negative number divided by 0 will give you minus infinity. And tan inverse of minus infinity, naturally delta will be minus pi by 2 radian. And when delta is minus pi by 2, put it here, then mod of that will become plus pi by 2. So omega t plus pi by 2. Here only omega t, here omega t plus pi by 2. So current is leading ahead in phase, and as such also I told you, whenever delta is negative, voltage is lagging behind in phase. Only capacitor is there, so these two are 0, and minus Xc whole square will be plus Xc square, its square root will be Xc, Xc means 1 upon omega c. Fine. What about phase diagram? These two are not there, so don't show XL, don't show R, only capacitor is there, so you are supposed to draw only Xc, correct? And wherever value of Xc is getting over, that there only you should write capital H, and extending ray OH, you will get voltage phasor. So situation is like this. This is, come on, current phasor, and this is voltage phasor. Come on, this is current phasor, this is voltage phasor. What is this angle between them? This angle is pi by 2 radian, correct? But because that angle is in fourth quadrant, I should take delta equals to minus pi by 2 radian. Delta equals to minus pi by 2 radian. Fine. For delta equals to minus pi by 2 radian, these are the graphs in which you can see when voltage is maximum, current is 0. But when voltage becomes 0, current becomes maximum on negative side. Then when voltage becomes maximum, current becomes 0. When voltage becomes 0, current becomes maximum. When voltage becomes maximum, current becomes 0. Now these are the oscillations. Look, when voltage is maximum, current is 0. But when this becomes 0, this becomes maximum on negative side. When this becomes maximum, this becomes 0. When this becomes 0, this becomes maximum. When this becomes maximum, this becomes 0, like that. So voltage and current are said to be oscillating with a phase difference between them minus pi by 2 radian. Fine. Now let us consider circuit number 6, in which R and L are in series, means capacitor is not there. If capacitor is not there, so this is not there. So positive number divided by positive number will give you positive number, tan inverse of positive number, tan inverse of positive number, so delta will be positive, delta will be positive. And whenever delta is positive, voltage is leading ahead in phase. Fine. What about change here? You are talking about circuit number 6, in which R and L are in series, means capacitor is not there. So X is 0, X is 0. So under root of R square plus XL square, but XL is omega L, its square will be omega square L square. What about phase diagram? Capacitor is not there, so don't show Xc, you can just show R and XL, correct? And then wherever value of XL is over, from that point onwards you can draw horizontal line segment, and through this point you can just draw vertical line segment, and wherever both the line segments intersect, there you will get point H. You can refer in the notes. Circuit number 6. Come on, do you find point H over here? Yes, it is there. And just extend line segment OH or draw ray OH. That ray OH will give you voltage phasor, and here it is current phasor. So whichever phasor is lying above on the upper side is said to be having higher phase. So voltage phase is more, voltage is leading ahead in phase. Come on, what about graphs? Whenever delta is positive, this sort of graphs you are supposed to draw, in which voltage becomes 0 first. So voltage is leading ahead in phase. Go for circuit number 7. L and C are in series, where XL greater than XC. Whenever L and C are together present in the circuit, you must compare their magnitudes of the reactances between XL and XC. You can make comparison 3 ways. XL equal to XC, at that time resonance will take place. Remaining 2 possibilities we are going to discuss right now. XL greater than XC, XL less than XC. Right now XL greater than XC. Look, resistance is not there, so R is 0. But XL greater than XC, bigger minus smaller, this number will be positive. Positive upon 0 plus infinity, tan inverse of plus infinity, then delta is plus pi by 2 radian. When delta is plus pi by 2 radian, put it here. When delta is plus pi by 2, this current formula will be I equals to Im cos of omega t minus pi by 2. In short, when delta is plus pi by 2, delta is positive, voltage is leading ahead in phase. And when resistance is not there, you can put R equal to 0. under root of XL minus XC whole square will give you XL minus XC, correct? Fine. Now tell me, what about this phase diagram? When resistance is not there, don't show R. Just to show XL and XC such that condition XL greater than XC is satisfied. Just to show this value say 7 units, this value say 3 units, 7 minus 3 will be 4. So this will give you XL minus XC. There only you must put point H. Refer circuit number 7. Do you find point H over here? Is it there? Fine. Now extend this ray. Ray OH will give you voltage phasor. This is current phasor. The angle between this voltage phasor and current phasor, you can see it is plus pi by 2 radian. In the first quadrant, delta is plus pi by 2 radian. Got it? Fine. And for delta equals to plus pi by 2, these are the graphs. Okay? Fine. Then we go for circuit number 8. L and C are in series, but XL less than XC. XL less than XC. When XL is less than XC, smaller number minus bigger number will give you negative number, and R is not there. So negative number divided by 0 will give you minus infinity, tan inverse of minus infinity, naturally delta will be minus pi by 2 radian. Put delta equals to minus pi by 2 radian here, then when you take modulus will become plus pi by 2. So here phase will be omega t plus pi by 2, which is greater than this phase by amount pi by 2 radian. Whenever delta is negative, voltage is lagging behind in phase. Fine. And when R is not there, you just write R equal to 0 and then under root of XL minus XC whole square, that will give you XL minus XC. But simply don't write XL minus XC, put it in a sign of modulus, because left hand side is modulus, it must be positive. And right now XL is less than XC, so if you write only XL minus XC, it will be negative. Better you put it in the sign of modulus. Fine. Now, what about phase diagram? XL less than XC. So this you can show say by 3 units, this you can show by say 7 units. Now ultimately we are supposed to take XL minus XC. 3 minus 7, so it is minus 4. And when it is minus 4, minus 1, minus 2, minus 3, minus 4, and there only you can write point H. Then find out ray OH, that will give you voltage phasor. It will be vertically downwards, and this is already current phasor. Angle between these two, you can see it is minus pi by 2 radian. Why minus? Because it is in the fourth quadrant, that's why. If this delta is in the fourth quadrant, then it should be taken negative. Fine. Now for delta equals to minus pi by 2 radian, these are the graphs. Okay? Come on. We go for now circuit number 9, in which C and R are in series. C and R means inductor is not there. When inductor is not there, XL is 0. XL is 0. And now negative number divided by positive number will give you negative number. When it is tan inverse of negative number, tan inverse of negative number here, tan inverse of negative number, then delta is negative. Delta is negative. Fine. When delta is negative, voltage is lagging behind in phase. Voltage is lagging behind in phase. You can check it from here. Whenever delta is negative, use this formula. When delta is negative, its modulus will be positive. So this phase will be more than omega t. So phase of current is more, means phase of voltage is less, means voltage is lagging behind in phase. You are talking about C and R in series, no inductor, so XL is 0, and minus XC square will be plus XC square under root of R square plus XC square, where XC is 1 upon omega C. XC is 1 upon omega C. Fine. What about this phase diagram? Inductor is not there, so XL is not to be shown. Just to show R and XC, and then from this point onwards you should draw horizontal line segment. From this point onwards you should draw vertical line segment, and wherever both the line segments intersect, at that point you should put capital H, that is hybrid point, and then ray OH you can find out voltage phasor, and angle between voltage phasor and current phasor will give you phase difference delta, which will appear in the fourth quadrant. You see in the notes, Refer circuit number 9. Do you find delta here in the fourth quadrant? Correct. Now tell me, for delta which is negative, which are the graphs? These are the graphs. In these graphs, if you just move towards the right hand side, from maximum value, if you start and if you move towards the right hand side, then this current becomes 0 first. If current becomes 0 first, means current is leading ahead in phase. When current is leading, voltage is said to be lagging behind. Okay, fine. And now tell me, these were the 9 circuits in which components were connected in series. And now another 2 circuits we will consider in which all the components are not connected in series. I am showing you what is the difference I am showing you. Consider circuit number 10, are in series with parallel combination of L and C. And here at present in circuit number 10, we will consider this case, XL greater than XC. Look, this is inductor, this is capacitor, this is resistor. You can see the inductor and capacitor, they are connected in parallel, and their parallel combination is connected in series with this resistance. Okay. Tell me the formula of inductive reactance. It was ZL equals to J omega L. ZL equals to J omega L. What about capacitive reactance? ZC equals to minus J upon omega C. Fine. And now let us do one thing. First of all, let us find out equivalent reactance of these two connected in parallel. And whatever equivalent reactance we will obtain, we will simply connect this R in series with that equivalent reactance. Okay. Let us proceed step by step. First of all, find out equivalent reactance of these two connected in parallel. There are 2 reactances. One is ZL, another is ZC. Only 2 reactances are there connected in parallel. Then what is equivalent? Multiplication upon addition. Multiplication upon addition. Look, ZL into ZC upon ZL plus ZC. Fine. That equivalent reactance are shown by symbol Z1. Fine. What is the formula of ZL? J omega L. Formula of ZL is J omega L. Formula of ZC minus J upon omega C. Minus J upon omega C. Formula of ZL J omega L. Formula of ZC minus J upon omega C. Come on. Minus J into J will give you minus J square. Minus J square means plus 1 because J square equals to minus 1. Minus J square is plus 1. Omega omega will cancel, giving you L upon C. Here it is L upon C. Okay. From these two terms you can take J common. When you take J common, inside the bracket it will be omega L minus 1 upon omega C. Fine. Now just multiply numerator and denominator by J. If you do that, here you have to multiply by J. So J into L upon C. When you multiply by J here, J into J will be J square. J square equals to minus 1. Because it is minus 1, if you multiply inside, order will be reversed. 1 upon omega C minus omega L. Fine. And now multiply each term, numerator and denominator, by C upon L. By C upon L. If you multiply by C upon L, C will cancel, L will cancel, giving you J. Here it is. Correct? Then if you multiply by C upon L here, C upon L, C will cancel, 1 upon omega L. Here it is, 1 upon omega L. Correct? When you multiply C upon L here, C upon L, then LL will cancel, giving you minus omega C. Here it is, minus omega C. Correct? But mind well, this is equivalent reactance out of parallel combination of ZL and ZC. But with that equivalent reactance, you can see R is there in series. So I must add R with Z1. Then I will get complex impedance of entire AC circuit. Fine. So that is Z equals to R plus Z1, R as it is, plus Z1, same value I have written here. I have just written this J as a multiplier. And inside the bracket I have written 1 upon omega L minus omega C. 1 upon omega L minus omega C, correct? Could you notice something? I have separated real and imaginary parts. Come on, without J, this R is real part, coefficient of plus J is imaginary part, okay? My dears, whenever L and C are together, I told you to have comparison between magnitudes of their reactances. At present, we take XL greater than XC, XL greater than XC. What is XL? Omega L. Greater than, what is XC? 1 upon omega C. Fine. Now transfer this omega C, transfer this omega L. Omega C will be greater than 1 upon omega L. Omega C will be greater than 1 upon omega L. Fine. My dears, up till now, what was the formula of delta? Delta was tan inverse of XL minus XC upon R. But now don't use that formula, because that was the formula of delta only in case of the series AC circuits. But here these two components are connected in parallel. Don't apply that formula. Then just go back and recall original formula. Original formula was tan theta equals to y upon x. What was y? Imaginary part. What was x in the denominator? Real part. Use that formula. Tan theta, instead of theta we put delta. Tan delta equals to imaginary part upon real part. Now tell me, for this complex impedance, what is imaginary part? This much. What is real part? This much. So as I said, delta equals to tan inverse of imaginary part upon real part. Tan inverse of imaginary part is this much. 1 upon omega L minus omega C. 1 upon omega L minus omega C. That divided by real part, which is R. And at present, because omega C is greater than 1 upon omega L, because omega C is greater, smaller minus greater will give you negative number. Positive upon negative, negative. Negative upon positive, negative. Tan inverse of negative number, tan inverse of negative number, then delta is negative. Delta is negative. Delta is negative, that is less than 0. Whenever delta is negative, voltage is lagging behind in phase. Voltage is lagging behind in phase. And now what about mod Z? Mod Z we can find out from here. Come on. How we do write magnitude of complex impedance? Square root of summation of squares of real and imaginary parts. So under root of R square plus 1 upon omega minus omega C whole square. Correct? What about phase diagram? In case of phase diagram, value of R is to be shown on positive x-axis, but value of imaginary part is to be shown on y-axis. Right now this is imaginary part, and in that if omega C is greater, then this value will be negative. If imaginary part is negative, just show it below origin. Had it been positive, we can show it above origin. Right now it is negative, so we show below origin. Now tell me, if this is value of imaginary part, this is value of real part, just extend from here, draw horizontal line segment, come on from here vertical line segment, and where both the line segments intersect, there we will get hybrid point capital H. And if you just find ray OH, it will give you voltage phasor, voltage phasor. So this is the voltage phasor, this is the current phasor, always in the direction of positive x-axis. Then this much is the phase difference between them, that is delta. Got it? And because right now delta is negative, we get it in the fourth quadrant. And now we go for circuit number 11. Same circuit but with a reverse condition. Earlier we had taken XL greater than XC. Now we take XL less than XC. Okay? If XL is less than XC, if the result is, if the condition is opposite to this, then ultimately you will get opposite condition to this. Opposite to this means what? Omega C less than 1 upon omega L. Omega C less than 1 upon omega L. If omega C is less than 1 upon omega L, then greater minus smaller will give you positive number, positive upon positive, positive, positive upon positive, positive. Tan inverse of positive number, then delta will be positive. When delta is positive, voltage is leading ahead in phase. When voltage is leading ahead in phase, at that time in the phase diagram, what the change you will make? Because this is the imaginary part which is right now positive, you must show it above origin, correct? On y-axis but above origin. Once this imaginary part is shown above origin, you will get this point H in the first quadrant, and then ray OH if you extend, you refer in the notes. See the last circuit, circuit number 11. Do get this point H in the first quadrant, yes. Ray OH is in the first quadrant, and this is the voltage phasor, this is the current phasor. Angle between them, that is delta, will be positive, and it is in the first quadrant. Got it? Fine. With that, we finish the all circuit analysis for all 11 circuits. Okay? Thank you. Come on, my dears. First of all, let us see what do we mean by average value of a particular function. At present, we consider function of time, and that function of time is shown mathematically by such a symbol f as a function of t, correct? We are interested in finding out its average value. So, let us take average, okay, fine. But how to find that average value? First of all, decide in which time interval do you want average value. Suppose I want average value in one periodic time. How much? In one periodic time. That's why I have taken time interval from 0 to capital T, correct? Then what you should do? At each instant of time in this time interval, you should find out instantaneous values of that function, and then you should take the addition of all those values. Addition or summation means an integration, correct? From 0 to capital T, from 0 to capital T. And then that summation should be divided by same time interval, that is t. If you do that, then such a ratio will give you average value of that function in this much time interval. Not necessary that you should find out average value in one periodic time interval only, not necessary. You may find out say from 0 to t by 2 suppose. Then in that case, here this integration should be taken from 0 to t by 2. But mind well, at that time here you should divide by t by 2. If you are finding average value in t by 4 time interval, then here integration 0 to t by 4, and here you should divide by t by 4. Correct? Fine. Now what do you mean by RMS value of alternating voltage? Wait. In semester 3, you had studied about voltmeter. Remembered? But that voltmeter was capable for measuring only DC voltage. It can be used only in DC circuit. But if the same voltmeter, if it is connected in AC circuit, we cannot take any reading, because in case of alternating voltage, you know the value of voltage and the polarity of voltage goes on changing periodically. And that's why if you connect that voltmeter into AC circuit, then pointer in that voltmeter would continuously deflect, would vibrate, will not become steady. We cannot take any observation, we cannot find out such a voltage. So in practice, to measure alternating voltage, we have designed special type of voltmeter, but that special type of voltmeter measures specifically defined average value of alternating voltage, and that specifically defined average value itself is known as RMS voltage. What is it called? RMS voltage. What do you mean by RMS? I am showing you. Look, first of all, in one periodic time interval, you find out instantaneous values of voltages, then make them squared, and then find out their average, and then take square root. Now tell me, which mathematical process you have undergone here? Root mean square voltage. I repeat, root mean square voltage. That's why it is shown by such a symbol VRMS, root mean square voltage. Got it? Fine. Now tell me, alternating voltage. The formula we know, V equals to Vm cos of omega t. V equals to Vm cos of omega t. Fine. make them squared on both the sides. V square will be Vm square cos square omega t. Fine. Now let us find out average value on both the sides. Come on, take average here. So average of V square, here Vm square is constant, and here if you find out average of cos square omega t, correct? Fine. Now this part as it is, Vm square as it is, but average of what? Cos square omega t. If omega t is taken as theta suppose, then you know formula of cos square theta. What is it? 1 plus cos 2 theta by 2. 1 plus cos 2 theta by 2. In short, 1 plus cos double by 2. 1 plus cos double than this, it is 2 omega t by 2. Got it? Fine. Now this Vm square as it is. Correct? This divided by 2 I have taken here. So Vm square upon 2. Then 1 as it is a constant, and you should go for finding average in this part now, average of cos of 2 omega t. Now Vm square upon 2 as it is, 1 as it is, but don't you know average value of sine or cosine function over one periodic time is 0. So this value is 0. So now it is Vm square upon 2 only. Take under root on both the sides. Come on, square root of this, and here when you take square root of Vm square is Vm, square root of 2 is under root 2. But what is this? Root mean square voltage. Root mean square voltage. That's why symbol is Vrms. Got it? What is Vrms formula? Vm upon root 2. Mind well, in the numericals, there are three types of voltages: instantaneous, maximum and RMS. I repeat, instantaneous, maximum and RMS. If it is instantaneous voltage, they will mention. If it is maximum voltage, then also they will mention. But in case of RMS voltage, sometimes they mention, sometimes they do not mention. If they say simply AC voltage, you must understand it is RMS value of AC voltage. Got it? Only voltage means RMS voltage. Got it? At our houses, you know Torrent Power Limited, that company provides electrical power. You know the value of RMS voltage at our residences? It is 230 volt, 230 volt, 230 volt. That is the RMS value of AC voltage in the power delivered at our home. Got it? Fine. Now we go for RMS value of alternating current. Now come on, wherever it is V here, there you should write now I. If you do that, come on, here you will read I RMS, and that equals to under root of average of I square. Instead of V, when you write I, come on, I RMS equals to under root of average of I square. Correct? Fine. Root mean square current. Root means square current. Correct? Fine. Come on, recall the formula of alternating current. Today only we had derived in the initial part of the lecture. I equals to Im cos of omega t minus delta. Take square, it will be now I square will be equal to Im square into cos square omega t minus delta. Correct? And now take average of I square. Here Im square is constant. Take average in this part, average of cos square of omega t minus delta. Fine. Now this Im square as it is. Correct? But don't you know formula of cos square theta? What is it? 1 plus cos 2 theta by 2. In short, 1 plus cos double by 2. 1 plus cos double than this. Double than this, it would be 2 omega t minus 2 delta upon 2. Now take this 2 with Im square. So it is now Im square upon 2. Inside the bracket 1. And now this average should be taken with this part, which can change with time. Come on, 1 is constant as it is, average of this part. But again, over one periodic time, the average value of cosine function is 0. So when this value is 0, come on, 0 plus 1 is 1. 1 into this is this, Im square upon 2. Take square root on both the sides. Square root of this are written here, square root of this, come on, Im upon root 2. Im upon root 2. What is this? Square root mean square current. Everybody, root mean square current. That's why I'm putting the symbol I RMS, and that equals to Im upon root 2. Vrms is Vm by root 2. IRMS is Im by root 2. Simple. Now we go for very good article about series resonance in series RLC AC circuit. Don't you know formula of maximum current? Maximum current equals to maximum voltage upon resistance according to Ohm's law. Maximum current equals to maximum voltage upon resistance. But so far effective resistance of AC circuit is concerned, we have given another name, and that name is magnitude of complex impedance, shown by symbol mod Z. Fine. Now divide on both the sides by root 2. If you divide by root 2, it will become Im upon root 2. Here Vm upon root 2 divided by mod Z. But what is Im upon root 2? Im upon root 2 is nothing but IRMS. Vm upon root 2 is nothing but Vrms. Put it here. Im upon root 2 is IRMS. Vm upon root 2 is Vrms upon mod Z as it is. Got it? Come on, Vrms as it is. What about formula for mod Z? Today in the initial part of the lecture, we have obtained mod Z formula under root of R square plus omega L minus 1 upon omega C whole square. Under root of R square plus omega L minus 1 upon omega C whole square. Now tell me, under given circumstances, Vrms is constant, and suppose we keep resistance also constant, suppose, and L and C are also constants, simply we change only omega, that is, we change only angular frequency of AC source. When you change omega, naturally IRMS will change. Now this part appears in denominator, so when this part will decrease, IRMS will increase. Suppose this part becomes 0, this part becomes 0 for particular value of omega, say at omega 0. Suppose this part becomes 0. 0 means minimum. When this value will become minimum, naturally this will become maximum. That's why I am putting here IRMS equals to maximum. But mind well, this part becomes 0 only for particular value of omega. Let it be shown by symbol omega 0. So now tell me, at particular value of angular frequency of AC source, it so happens that value of RMS value of current passing in the AC circuit becomes maximum. Such a phenomenon is known as series resonance. Why it is called series resonance? Because right now we have connected all the components in AC circuit in series. There is a talk of parallel resonance also in the numericals, but in the theoretical part we have to discuss only for series resonance. Okay, how would you define it? In a given AC circuit, when angular frequency of AC source is made equal to particular value, at that time the phenomenon of RMS value of current to become maximum is known as series resonance taking place in that circuit, and that particular value of angular frequency is called series resonant angular frequency of that AC circuit, shown by symbol omega 0. And tell me, what is this? Omega L minus 1 upon omega C. Omega L minus 1 upon omega C, remembered? It was imaginary part of complex impedance. Imaginary part of complex impedance. In any AC circuit connected, I am talking about series AC circuit. In any series AC circuit, when imaginary part of complex impedance becomes 0, phenomenon of RMS value of current becoming maximum is known as series resonance, and particular value of angular frequency at which this imaginary part becomes 0 is known as series resonant angular frequency. Series resonant angular frequency. Now let us obtain formula of omega 0. Just transfer this. When you transfer this over here, it becomes plus. So omega 0 L equals to 1 upon omega 0 C. Correct? Transfer this omega 0 here, transfer this L in the denominator. So omega 0 to omega 0 will become omega 0 square, and here 1 upon LC, 1 upon LC. Take now square root on both the sides. Square root of this is omega 0, square root of this is 1 upon under root LC. Got it? Now tell me, what is formula of omega? 2 pi f. But if it is omega 0, then you should write 2 pi f0. And right hand side as it is, transfer this 2 pi in the denominator. So f0 will be 1 upon 2 pi into under root of L into C. This is called series resonant frequency. Omega 0 is called series resonant angular frequency. What is the difference in the unit? Unit of frequency is hertz, unit of angular frequency is radian per second. Got it? Let us see now what is called series resonance curve. In a given series AC circuit, if you go on changing omega, naturally IRMS will change. You just note down the corresponding values of IRMS and then plot a graph of IRMS versus omega. Such a graph is known as resonance curve, series resonance curve. If you keep value of resistance equal to R1, then suppose we are getting such a resonance curve, and then if you keep higher resistance, then current decreases and the graph is like this, correct? This is the graph for value of resistance R2, where R2 is greater than R1 because R1 is less than R2. Fine. Such graphs are known as series resonance curves. First of all, tell me, what does this graph indicate? This graph indicates that initially when this angular frequency increases, come on, value of IRMS goes on increasing, correct? Then at this peak point it becomes maximum, say IRMS maximum, and then after when value of omega is increased beyond omega 0, then value of IRMS goes on decreasing. Fine. Similar is such a graph, correct, for higher resistance. Both of these curves are called resonance curves. Okay. Now do one thing. You just divide this value by root 2. IRMS maximum I am dividing by root 2. When you divide by root 2, the value will become nearly 70%. If this value is 100%, then this value is nearly 70%. Now just draw one horizontal line. Okay. That horizontal line will intersect this resonance curve at these 2 points, say points A and B. At point A, suppose value of omega is equal to omega 1. At point B, value of omega is suppose omega 2. Now, if you want to find out this much width, how much AB, then you should take omega 2 minus omega 1, omega 2 minus omega 1. And that omega 2 minus omega 1, it is delta omega, and that delta omega is given specific name. That specific name is half power bandwidth. Delta omega is called half power bandwidth. Delta omega is called half power bandwidth. Come on, half power bandwidth. You may ask why it is called half power bandwidth. What is reason? Reason I am showing you. Here the value of current is IRMS maximum, and here value of current is IRMS maximum upon root 2. Suppose I take this current as I. At current I, what is the power? Come on, P equals to I square R. And now instead of I am suppose passing current I by root 2 in the circuit. So this is taken as I by root 2, I by root 2. At that time new power I am showing by symbol P dash. Now instead of I am just passing current I by root 2, its square into R. So this is I square R upon root 2 square. Root 2 square is nothing but 2. But wherever it is I square R, I can write P. So write here P. So it is now P by 2, P by 2. So P dash equals to P by 2, P dash equals to P by 2. P by 2 means half of P. So this power has been reduced to half of initial value, half of initial value. That's why we call such width as half power bandwidth, shown by symbol delta omega. So delta omega is omega 2 minus omega 1, or you can say it is width AB, width AB, fine. And now compared to this resonance curve is more sharper. Sharpness of this curve is more than sharpness of this curve, correct? But just to have measure of sharpness of resonance curve, we have defined a new physical quantity. It is called Q factor. What is it called? Q factor. And it is defined this way: ratio of series resonant angular frequency for given series RLC AC circuit to the corresponding half power bandwidth is called Q factor of that circuit. Q factor of that circuit. Now this is unitless because it is angular frequency upon angular frequency, it is unitless. Okay. Now omega 0 as it is, there is a formula of delta omega, not in your syllabus. Derivation is not there in your syllabus. Just remember, formula is very simple. Formula of delta omega, just remember R upon L. Denominator will become numerator. So omega 0 into L upon R. And now Q as it is, correct? Now what is omega 0 formula? Omega 0 is 1 upon under root LC. Omega 0 is 1 upon under root LC into L upon R, into L upon R. Now tell me, this L can be written as under root L into under root L. L can be written as under root L into under root L. So 1 under root L will be getting cancelled. And then left is 1 upon R as it is, under root L upon under root C. Altogether you can write under root of L upon C. So there is second formula for Q factor. Please remember, Q equals to 1 upon R into under root of L upon C. Now my dears, at home, I am just giving you one little exercise. Just write, you will really enjoy. Come on, write the units of all these quantities. Come on, resistance unit is ohm, inductance unit is Henry, capacitance unit is farad. Write all these units, simplify and prove that Q factor is unitless. I will show you in the next period, I will show you the easiest, shortest way to prove that Q factor is unitless. Okay, fine. Now tell me, how many points are noteworthy at the time of resonance? I am showing you. At the time of resonance, at the time of series resonance, first, angular frequency of AC source has become definite, and that definite value is just equal to omega 0, whose formula is 1 upon under root LC. Omega 0 equals to 1 upon under root LC. Second point, value of IRMS becomes maximum. Fine. What about complex, what about imaginary part of complex impedance? Imaginary part of complex impedance becomes 0. Imaginary part of complex impedance becomes 0. Now transfer this. When you transfer from minus, it will become plus. What is omega L? Omega L is nothing but magnitude of inductive reactance. It was shown by symbol XL. What is 1 upon omega C? Magnitude of capacitive reactance, shown by symbol XC. I mean to say, at the time of series resonance, inductive reactance, magnitudes of inductive reactance and capacitive reactance have become equal because XL equals to XC. Now tell me, what was the formula for mod Z? Formula was under root of R square plus XL minus XC whole square. At the time of resonance, when XL becomes equals to XC, this part will become 0. When this is 0, at that time mod Z will become minimum. When this is 0, under root of R square will be only R. So value of mod Z becomes minimum equal to R. And because of minimum resistance, maximum power is transferred between source and the circuit. Maximum power is transferred. So power consumption is maximum. Okay. These are the noteworthy points. Now last one point, sharpness of resonance curve. Compared to this resonance curve, sharpness of this resonance curve is more. But compared to this bandwidth is shorter, smaller. When this bandwidth will decrease, Q factor will increase. So Q factor of this curve is more and its sharpness is also more. So greater is the sharpness, greater is the Q factor. Speak reverse. Come on. Smaller is the sharpness, smaller is the Q factor. Greater is the sharpness, greater is the Q factor. Smaller is the sharpness, smaller is the Q factor. Thus, Q factor gives measure of sharpness of resonance curve. Q factor gives measure of sharpness of resonance curve. Okay. Then we go for tuning and selectivity. My dears, all of you have tried how to tune a radio, correct? You know what are you doing at that time? When you are tuning the radio, at that time, you are changing this angular frequency by changing either only inductance or only capacitance or both of them. Ultimately, you are changing omega 0. By changing omega 0, you just set it equal to omega. When omega equals to omega 0, then f equals to f0. F equals to f0. You know what is that f? F is the frequency of radio waves which are coming to the antenna of your radio. When those two frequencies will become equal, at that time value of current passing through the circuit will become maximum. If maximum current passes in the radio circuit, it will give you very loud and clear sound. At that time we say the tuning is over. Tuning is over. Okay. And any circuit which is having less half power bandwidth, means more Q factor, and if Q factor is greater, then its selectivity is also greater, and then quality of the radio is also better, which consumes ultimately in terms of money, correct? If the quality of the radio is better, then naturally it will be more costly. Okay, so remember, tuning and selectivity are the two quality deciding factors of a radio. Okay.